Start this third Coloquio of Categories Álgebras here in Oaxaca. And we would like to thank to the organizers for this. For the first talk, we are going to have Dominic Verity. He's going to talk us about the synthetic infinite category in infinite cosmology.
So thank you very much for inviting me here to Oaxaca. So I should apologize because I only arrived yesterday at about 8 p.m. after 24 hours of flying. So I haven't actually slept yet. So if I sort of fall asleep halfway through the talk, it's not commentary necessarily on the content. My name is Dominic Verity. I'm a member of the category theory research group at Macquarie University in Sydney. I guess the home of Australian category theory. And this is joint work with Emily Reel, who's at Johns Hopkins University. And I guess maybe what I'm going to talk about is bringing Australian-style category, or bringing the way that Australian category theorists think about the world to infinity category theory. And certainly when I first started thinking about infinity category theory about 10 years ago, I found it an amazingly stressful and irritating subject, because one of the things that people would never tell me is, well, why is this category theory? So they would do lots of things, and if you've read Jacob Murray's book, he proves lots of results. But for a category theorist, trying to understand these results as actual category theory rather than as a piece of applied algebraic topology or something was quite difficult for me. And he kept doing things that I felt needed to be better motivated in category theory. So this is really what this program is about. The other part of the program is, as you'll see as we go through, is to give I guess a broader perspective on infinity categories. So one of the problems in the infinity category world is that when people say, I have an infinity category, they generally mean a different thing. So there are many models of what it means to be an infinity category. There are many more models of what it means to be an infinity n category. And in any particular case, when somebody says, I've got an infinity category, they might mean any one of those models. And some of those models are well developed from a categorical perspective and others aren't. So part of this is to try and give a framework that allows you to understand the category theory of many of these different models without having to think too hard about a specific model at a particular time. So for instance, if you're familiar with quasi-category theory, you should be able to understand this, but you should then be able to apply it to, say, the category theory of complete Siegel spaces. So the aim, I guess, of this work and of this talk is to give a precise and model-independent account of infinity category theory. And I should say that what I'm not trying to do at all is show that all of these models of infinity categories are the same. What I'm trying to do is give a methodological approach to understanding the category theory of a whole bunch of different models that may actually be quite different. If you're interested in following this after this talk further, there are a couple of resources that you might want to look at. One of them is a thing that we wrote in 2016 called Infinity Category Theory from Scratch, which was an attempt to make this a little bit more accessible. Something that's more recent is a book that we're about 490 pages into writing called The Elements of Infinity Category Theory. And we're hoping that that will be complete by the end of this year. But certainly everything that I say in this talk is contained in that draft, in one form or another. So what are we actually going to do? So first of all, I guess we should think about what an infinity one category is supposed to be. And we'll not worry at this stage too much about giving precise definitions of these things. So on the schematic side, the definition is that an infinity one category is supposed to be a category weakly enriched in spaces. So imagine that you have a category that has a set of objects, and between each pair of objects, there is a space of maps. But then when we come to composing those maps together. We might be able to compose them, but we can't assume that that composition is associative. All we can assume is that it's associative up to some kind of homotopy. And then, of course, once we started sort of wiggling things using homotopies, then we need to assume that those homotopies are themselves coherent. So we probably need to have higher homotopies in these structures and so forth. And maybe the way that we think of our spaces, and spaces is a sort of very general notion, but we might think of them as infinity groupoids or just normal topological spaces, or for us actually let's talk simplicial sets. So the kinds of models that you'll hear people talking about when they talk about infinity categories, the most popular ones are these things called quasi-categories, and we will talk a little bit about those during this talk. There are things called complete Siegel spaces. So both of those models are based upon simplicial sets. So in the first case, I have a simplicial set that has a particular property, and we call it a quasi-category. In the second, we actually take doubly simplicial sets, and in one direction of our double simplicial set, we think of things spatially, in the other direction, we think of them as weakly categorical. And we can build a similar kind of theory there. There are Siegel categories, which are slightly weaker than complete Siegel spaces, marked quasi-categories, and a range of other things that we'll see as we go through this talk. But these are probably the ones that are most familiar to people. One thing that I should say, something that particularly interests me, is that we're not only interested in these specific models of infinity category theory, which probably most people, well, we know that there are theorems that give us equivalencies between these theories, so passing between them along those equivalencies should be relatively easy. But the category theory I'm going to develop should also, for instance, apply to fibered variants of these. So as category theorists, we're interested in saying, I'm going to start with some base category, and I'm going to consider categories that vary over that base category. So maybe we have some kind of growth and defibration sitting above that category, and I want to build a fibered variant of category theory that allows me to talk about doing category theory in fibers. And that's certainly a very important theme in category theory and also in the application domains for this work. And what we'll find is that the theory that we develop will apply perfectly happily to fibered variants and all sorts of other things. So the idea is that we're going to capture some of these models, and we're going to talk about their category theory. One thing, as I say, we're not going to do is we're not going to prove that these models are equivalent, because I don't actually care. All I care about is that each of these models supports a category theory, and we're going to describe how the category theory works, or at least a fragment of how that category theory works. There are some auxiliary aims in this work. So one of them, for me, is to build a framework that can be extended to give foundations to the category theory of infinity n categories. So in the same way that categories can be extended to strict n categories, we can extend the models for infinity categories to infinity n categories. And I'd like to at least get some insight out of this work about how the category theory of those structures might work. We know that we can at least get the basics of understanding how standard two category theory works by considering its theory as an enriched category theory, and so therefore we'd like to do a similar kind of thing here to understand some of these higher models. And the kind of models that we might be interested in there are things called complicial sets and iterator Siegel spaces and theta n sets and so forth, all of which fit at some level into this model. So what I'll do throughout this talk is I'll use the term infinity category for any structure that we might reasonably regard as having an infinity category theory. So it doesn't just mean infinity one categories, it also means the basic theory of infinity n categories. And in the case of complicial sets, it's a candidate model for a notion of infinity category. So an infinity category would be something that had non-invertible cells going all the way up through the dimensions. Okay, but I won't talk about complicial sets in this talk. So why might we want to take the approach that I'm going to suggest today? So the first thing is that we'd like to give synthetic proofs of infinity categorical results, which will then apply in all models. So if you look in the 1,000-page book of Jacob Lurie, he proves a lot of results about category theory, but he proves a lot of results about the category theory of quasi-categories. And there's a fair amount of effort. It's not entirely trivial to then take that work and turn it into the corresponding thing for, say, complete Siegel spaces. People have certainly done that. It's not impossible at all, but there's a lot of work involved going from one to the other, and we want to try and reduce that amount of work. So we'd like to give synthetic proofs of these things so that we don't have to keep doing that work every time we see a new model. I mean, I would say we're going to, we might imagine that maybe in some world all of these infinity category models will be equivalent, and I can translate along. Equivalence is that, of course, probably is only a dream, and certainly isn't true if we want to look at higher cases, or in the private cases that I talked about. So we need to do something like this. Secondly, I'd like to transfer categorical results derived analytically in one model to related models. So even if I know I've got an equivalence between two infinity category models, what does it mean to say that that equivalence preserves and reflects their category theory? So often the way that we posit those equivalences is in terms of equivalences of model categories. Equivalences of model categories certainly preserve and reflect the homotopy theory involved in these structures, but we need to ask in what sense do they preserve and reflect the category theory involved in those models. And in order to do that, we both have to define what category theory means in this context, and then we have to prove results about preservation along equivalences. But in fact, it is possible to do this kind of analytical derivation of results in situations where models are more weakly related. So you don't necessarily have to have an equivalence between two models to be able to infer something about the category theory in one from the category theory in another. So often an adjunction or equivalent adjunction or something like that will suffice to give you some information. Okay. And then lastly, because I come from Australia, my interest in this is to adapt and apply intuitions from meta-category theory or two-category theory to this context. So we want to take two categorical foundations and we want to turn it into something that we can actually apply in infinity category theory. And that's because I come from down here. So this is sort of about where Sydney is on a terrible hand-drawn map of Australia. And of course, the Sydney category theory seminar has been famous for many years for beavering away in complete isolation somewhere on the other side of the world with two categories and so forth. So in principle, this is something that we might know something about. Or at least, in principle, it's a competitive advantage that those of us who work in Sydney have, that it's useful to apply elsewhere. Okay, so how are we going to go about this? So the first thing I'm going to say is that in the same way that we think of categories as sitting in, certainly in Australia, we think of as categories as sitting inside two categories. So in other words, categories are the objects of the two category, the functors between them are the arrows, and then we have natural transformations between the functors, and those give us some kind of two-dimensional structure in the category of categories. And what happens in Australia is we then say, okay, well, let's see how we can do category theory in a situation where we just start off with a two-dimensional structure like that, and we add some axioms to it and see how much category theory we can get done. If we're going to do this, then probably what we have to accept is that the way to do infinity category theory is to recognize that infinity categories live inside infinity two categories. So that already sounds a bit scary. So the idea of an infinity two categories, it should be some kind of structure that has objects, and it has one-dimensional sort of arrows between them, and it has arrows between the arrows, and then it has some kind of higher structure going up. It's all invertible, it's homotopy structure that's going to allow us to understand the couple of elements of the 1, 0, 1, and 2-dimensional structure. So it's probably more natural to say that infinity two categories provide a natural meta framework in which to develop infinity category theory. But of course then we've got the problem that I've now got to explain to you what an infinity two category is before I even start explaining what an infinity category is. And that's possibly a slightly daunting aspect of this, especially since doing calculations inside infinity two categories is not necessarily fun. So let's see how we go about trying to make that a bit easier. So really, are we going to use infinity two categories? So the trick here is, first of all, to try and pick a model of infinity two categories that's familiar to most people. Well, to most people who've done some infinity category theory, unfortunately. But at least is going to be familiar to a growing group of people across the mathematical world. The second thing we're going to do is we're going to try and simplify as many arguments as we can by working inside a simpler structure called the homotopy 2 category. And the way to think about this is that often when we do, say, arguments in topology, we start off with a complex structure, we play around with it for a while, and we realize that the only way to understand the particular thing that we're interested in is to take some quotient of that structure. So maybe we do that by taking a space and taking its homotopy groups, or maybe more importantly, we take some kind of cohomology on the space. This represents a process of, I guess, quotienting the space, or at least throwing some of the information away that's contained within the space, but hoping to retain the information that we need for a particular argument within the simpler structure. And that's what we're going to do here. So I'm not going to claim that there's some kind of magical, nice, simple 2 category in which we can do every infinity categorical argument that we might want, but for many situations, we can get a lot of information about the nasty infinity 2 category that we want to work in by quotienting that and making it into a real 2 category in the form that, you know, people in Sydney and across the category theory world would have recognized from the 1960s. And then we can do some arguments in there. And in fact, what's really remarkable about this is that, much to my surprise, in fact, over the past 6 or 7 years, the range of things that we can do by making this quotient is unexpectedly large. I wouldn't have expected at the beginning that we could have done some of these things. So let me tell you a bit about what you can do. So the first thing I'm going to say very quickly is that we're going to commit to an infinity 2 categorical model which was suggested to us by Peter May we should call an infinity cosmos, because there's been a bit of a tradition of calling things a cosmos if it's a place in which to do category theory. So in the same way you have a topos, which was a place to do set theory, maybe a cosmos is a place that has some structure that allows us to do category theory. So this thing's called an infinity cosmos. Although Emily, I think, was at the Perimeter Institute in Canada last week and had a number of cosmologists come up and say they understand the word of their talk. So if anybody's expecting me to talk about the expansion of the universe, I'm not going to do any of that. Okay, so the particular structure that we're going to look at is really just, I mean, for those who are kind of familiar with the basic sort of infrastructure of categorical homotopy theory, the structure we're going to look at, an infinity cosmos, is simply a category of fibrant objects enriched in the Joyal model structure. Okay, so the important thing here is that the Joyal model structure is the model structure whose fibrant objects are quasi-categories. This structure is enriched in that. So what we should think of this as, these structures are enriched in quasi-categories. So infinity cosmoi are enriched categories, each of whose Hom spaces is a quasi-category, in the same way that the 2 category is a category enriched in categories. Okay. So in order to do infinity category theory, we can't just enrich our universe in categories, we have to enrich it in something else, and we have to enrich it in infinity categories. So, I mean, the point here is we are going to have to learn some infinity category theory, but in fact, you can develop the infinity category theory you need as you go through developing the theory of these things. But ultimately, it does rely on us making a commitment to one model, and then using that model to understand a whole range of other models that fit into this framework. Okay. So just think, we're just doing the simplest thing possible that we might think might work, which is if 2 categories work for category theory, then enriching in quasi-categories might work for infinity category theory. I guess in more detail, we could say that an infinity cosmos is sort of all of this information summarized on this slide. So first of all, it's just a simplicial category K, which is the universe we're going to work in. So in other words, this is just a category. Its Hom spaces are simplicial sets. And all of the composition that we're interested in, sort of the horizontal composition, and this is a genuinely enriched category. So there's some weakened stuff because the Homs are simplicial sets, but in terms of composition between Hom sets, that's just strictly associative composition. So There's nothing too difficult there. This is about the simplest model that we can think of for infinity 2 categories, because at least one of the compositions is strict. So the second thing that we need in these structures is the stuff about it being a category of fibrant objects. So really all that means is that we have a notion, this comes equipped with two classes, the isofibrations, or the fibrations in this structure, and weak equivalences. So we have certain maps that look like topological fibrations, although in fact in this context the way to think of them is the way that a category theorist would think of an isofibration. So an isofibration is a functor between categories in which we have a lifting property just on isomorphisms. So if I'm given an isomorphism, I'm given something at one end of it in the total space, I can lift that isomorphism up to an isomorphism here. And really the way to think of the fibrations in this thing is they are the well-behaved maps between infinity categories that admit isomorphism lifting. And we won't worry about them too much. Well, we will worry about them, but we'll not dwell on them too much in this talk. Secondly, we've got a notion of weak equivalence, which tells us what things are expected to be equivalent. We require a couple of other things, so we do require cofibrant replacement, and of course, all objects are going to be fibrant because this is a category of fibrant objects. But again, we won't worry. I mean, for this talk, the details of this are not actually fantastically important. And then we have the various properties that we might expect. So products and pullbacks of isofibrations work quite nicely. The fibration notion is stable under pullback. And then finally we have things called cotensors. So this is the action. So we've got a category that's enriched over simplicial sets, and we assume that simplicial sets in fact acts on that category in the sense that if I'm given an object in the category and I'm given a simplicial set, I can raise the object in the category to the power of the simplicial set in the usual sort of inverted categorical. And what that means in particular is that we'll see that, for instance, all limits in this structure that exist there are actually simplicially enriched limits. So they have the simplicial universal property that we expect rather than just a set-based one. But as I say, if this is already starting to get too confusing, don't worry about it, because we'll try and avoid talking about any of this structure. In fact, only much of what I'm going to say today is independent. This structure is one that's familiar to people, that people can calculate in, but many of the themes that we'll see today will work in any infinity 2 categorical model in a similar way. We don't need all of this structure to do it. Okay. And I'll just remind you what a quasi-category is. So a quasi-category, because we're enriching over quasi-categories, is just a simplicial set which satisfies a certain lifting property relative to specific horns, so specifically the inner horns. So the idea is, so of course, we're all familiar with the notion of a Kahn complex. So a Kahn complex has fillers for all horns. And we think of those fillers as determining both the compositional structure of the Kahn complex, so if I'm given two simplices, how I can compose them together. And we think of it as telling us about the invertibility properties of simplices, because in the Kahn complex we think of it as an infinity groupoid, so every cell in that groupoid has an inverse, and the outer horn fillers tell us that every simplex has in some sense an appropriate weak inverse up to horn. So what we do when we're talking about quasi-categories is we just think about Kahn complexes and we say, okay, well, if the outer horn fillers gave us something about the invertibility of everything, if we drop those, we end up with a structure in which we still have composition, but we don't have invertibility. And then the Joyard model structure is just a structure. A model is a structure that provides us with fibrations and with weak equivalences, and in particular it's a structure in which the fibrant objects are the quasi-categories. But the way to think about these quasi-categories is they're categories in which I have a notion of composition of the one simplices, but that composition is only associative up to some two-dimensional structure. And then that two-dimensional structure is itself coherent up to a three-dimensional structure, which is, and so forth. Okay. So we're enriching over this structure, and that's really where a lot of this structure here is about the interplay between the enrichment and this Joyal model structure. So one thing to note immediately is that these axioms have been designed so that if I take the fibrant objects in the Joyal model structure, then immediately that's enriched as a category of fibrant objects in the Joyal model structure itself. So it's immediately a model of this infinity cosmos, of these infinity cosmos axioms. I think I'll probably not worry too much about this axiom. And I'll just tell you that these structures encompass, so all of the things that I talked about in the first couple of slides. So models of this include quasi-categories, Siegel categories, complete Siegel spaces, marked quasi-categories. They include Siegel spaces, infinity n sets, n completial sets, and so forth, so a whole bunch of n-dimensional structures of this kind. They also, and one of the reasons from a categorical perspective, or from a two-categorical perspective, of starting with these structures, is that they also support, there's a whole range of constructions on infinity cosmoses that give us, again, infinity cosmoses. And that those constructions are used over and over again in describing the category theory of these structures. So one very important one is the notion of a slice. I can take an infinity cosmos and I can form a slice category of it, where I just restrict things slightly by saying that only things that I want to be mapped down. So I take an object, I look at maps down to it from all other objects, and I want to restrict those to be isofibrations. That's the only thing that I do. In other words, I want the thing sitting over my base thing to be well behaved, to have an iso lifting property. That enables me to use a strict slice rather than a weaker slice property here. So this is very important because in many cases in category theory, I'm not just interested, as we talked about earlier, with looking at relationships between categories. I'm actually interested in thinking of categories as sitting over another category. Many properties are described by saying such and such is a map in the slice over this. And that's an important piece of structure that we want to preserve here. So very importantly for us, slices, if I take a slice of infinity cosmos, it's again an infinity cosmos. The infinity category is fibered over a base, which is a sub-cosmos of that, is again a cosmos. Things like, if I take the collection, so we'll define what it means to be a complete or a co-complete infinity category as we go through this. If I take the collection of complete or co-complete infinity categories with the structure preserved in upstream, so things that preserve those limits or co-limits, then that again is an infinity cosmos. So as we'll see, maybe if we get to the end of this talk, for instance, stable infinity categories form an infinity cosmos and inherit a category theory from So all of the models, I mean, I guess that there are some models that you might hope fitted into this framework that don't. One of them is simplicially enriched or calm complex enriched categories. That doesn't fit into this framework. Another one is maybe relative categories, so categories that are just given a set of delegated equivalencies. Those don't fit into this framework. And that's because we've chosen this slightly more restrictive framework so that we can get some nice properties of sort of strict enrichment. Those certainly fit into infinity 2 categories, and we can describe the category theory of those infinity 2 categories. They just don't rectify easily into this slightly more restrictive. Okay. So how are we going to actually analyze this situation? So we've got a structure, it's complicated. I've got some nasty quasi-categories going on in the HOMS. I want to try and avoid. As soon as I start trying to think about, for instance, pasting together diagrams of 2 cells, where the composition of 2 cells is only defined up to homotopy, that starts to make, it's possible to do that, but it starts to make my head ache. So as far as possible, I want to avoid this. So a suggestion made actually by André Joyal, right back when he was first discussing what a quasi-category was to say, okay, well, what we can do is we can form a 2-category of simplicial sets. And he used the 2-category of simplicial sets to think about what was an equivalence of various other simple notions. So the way that we form a 2-category of simplicial sets is that we observe that there's an adjunction between simplicial sets on the right-hand side and categories on the left-hand side, where the right adjoint of this is the usual nillifunctor, And in fact, what I always say to my students is that all categories are simplicial sets. So, and the nerve functor is just an embedding. Whenever I think about a category, I think of it as a simplicial set, not as just a category. It's got higher structure, although for a category that's relatively trivial. And then, of course, that's got a left adjoint, which is called, I guess, the homotopy category functor. It's what you get by taking, so for instance, if you take a quasi-category on the right, the homotopy category of that quasi-category is the thing that has the same objects as the quasi-category, but has equivalence classes of one simplices as its arrows. And then once I've taken equivalence classes of one simplices under higher homotopy, those things are going to compose nicely and associate. So now, an important property of this H functor that allowed Joyal to define the two categories of simplicial sets is that H in general preserves products. So the products that are used in the definition of simplicial sets as an enriched category over simplicial sets. So what I can do is I can take simplicial sets, I can enrich it over itself, I can apply H to each of its Hom spaces. So that's going to give me something that has Hom spaces that are now categories. But of course what I need to worry about is, do I get any kind of composition between those Hom categories? And what that relies on is knowing that H preserves something to do with products. And in this particular case, it actually preserves products. We can go with weaker things, but we won't worry about that. So the fact that H preserves the products in certain and the products in cat actually means that if I'm given any simplicity enriched category, I can always make a category enriched category simply by applying H to each of its Homs. And that's what this functor down here does. So what I can do is I can take a simplicity enriched category, I can apply this H functor, this homotopy category functor to each one of its Hom spaces, which are simplicial sets. Then I can use the fact that H preserves products to enable me to show that the category structure on K as a simplicity enriched category gives me a two-category structure on here, a cat enriched category structure. So one thing that we can do is we can apply that construction, which we call the homotopy two-category construction, to an infinity cosmos, because an infinity cosmos is just something enriched in simplicial sets. In fact, what I'm going to do is I'm going to assume that in my infinity cosmos all of my objects are cofibrant. All that means is actually not only are its Homs simplicial sets, but all of its Homs are genuine quasi-categories. Again, that's not necessary, but it's helpful for some exposition. Okay, so what we can do is we can apply the previous construction to this, and what we get is a two-category. So that two-category has, as its objects, the cofibrant objects in K. As its one cells, it has arrows between the objects of K. So if you think about a simplicity enriched category, between each pair of objects, it has, well, I guess it has arrows of all dimensions. So it has zero-dimensional arrows, which are the zero simplices in the Hom, which are the usual thing that we just call arrows. It also has one-dimensional arrows, which are the one simplices in each Hom, and two-dimensional arrows, which are the two simplices in each Hom, and so forth. What we're going to do for the one cells is we're just going to take the arrows, the zero simplices in each Hom. We're not taking equivalence classes of those, we're just taking all of those arrows. But then what we do on the two cells is we actually take homotopy classes of one simplices in the Homs of the original category. So we're just applying that H construction on each of the Homs. So what we're doing is we're taking equivalence classes. So our two cells are now going to become equivalence classes of one simplices in the original category, or in other words, of arrows in the quasi-categories that make up its Homs. So, I mean, the first thing to expect is that this construction is not necessarily going to do nice things to the structure of K. So, of course, one of the reasons that we invented things like model category theory was the observation that if I start with the category of topological spaces and I take its homotopy category, so I quotient it out by homotopies in its Homs, then what I get is a category that is interesting. I mean, as homotopy theorists, that's the structure we claim that we're studying, but it hasn't got very much structure. I mean, it's got products, and it's got some kind of weak limit notion that's not particularly useful. And I mean, I guess the best structure that we can find on it is probably if we do this, if we sort of Abelianize this situation, then we get triangulated categories that seem to have much more structure that capture things that we can talk about. But there's not very much more structure than that. So what we tend to do is we tend not to try and work directly in the homotopy category. We work in the model category and we infer results about a homotopy category. What I'm going to suggest here is that actually this construction is somewhat better behaved than that, and it actually means that we can do a lot more inside here than we might expect from just our understanding of what happens in the traditional homotopy category case. So, for the purposes of this talk, the only thing that I'm going to look at is the notion of a junction between infinity categories. And I'm going to make a wild conjecture. So in the same way that Joyal said the way to capture the notion of equivalence between quasi-categories is to look at equivalences in this two category, I'm going to say that, well, actually more is true, that we can actually capture the correct notion of a junction between infinity categories by just considering the junctions in a two category. So, is everybody happy with what a junction is in a two category? Seems good. Because often what happens is I give this talk to people who are sort of predominantly topologists, and so they're happy with the talk up to this point. Right? And then when I say this thing's in a junction in a two, or even when I say it's a two category, they started to look a bit worried. And then when you say this isn't a junction in a two category, they go pale. So this is the part of the talk where I think things are getting easier, right? So maybe this project is doomed to failure if topologists think that it's difficult. So by an junction in a two category, I mean, of course, that we have a presentation of junctions in category theory that says I can give it by giving a pair of functors and a unit and a co-unit, and assuming that I have the triangle identities holding between the unit and the co-unit. Those, of course, are all equational conditions that can be expressed in any two category. And so by an junction in this case, I mean literally just the equational definition, the equational two category theorist definition of what the junction is, just interpreted inside some two category. In this case, it's this awful two category that we've constructed by taking an infinity two category and quotienting it down to give us a genuine two category. So if you believe that this is true right now, then you've got much more insight into this situation than I had when we started this project, because I really didn't believe that this was going to be the case. And so it goes to show that sometimes you should just wake up one morning and try a stupid idea, because sometimes stupid ideas work. Now, there are already clearly notions of a junction between infinity category that exist in the literature, notably the one given by Verity, which is given in terms of, well, in various forms, but in terms of defining what it means for something to be both a vibration and both a Grothendieck vibration and a Grothendieck-Opp vibration over the arrow, which I guess for category theorists corresponds to something about this looks like then what's called a collage of a profunctor, and really what this condition says is that that profunctor is both representable on the left and on the right. That's not, I mean, when you first read his work, understanding that that's what he's up to is not particularly clear to most people. And the hope is that by sort of positing this in at least something that's clear to two category theorists, that maybe we can understand this as a junction. And certainly, we know lots and lots of things about junctions in two categories. So if this is actually true, we can take anything we know about junctions in two categories and we can apply it to infinity category theory wherever we're doing it. Okay, so let's see whether this wild conjecture actually works. So the first thing to notice is that we might ask, well, does it work for, so we might work just in quasi-categories, or something that this slide works in any infinity cosmos. We might just ask, well, what does it mean to be, for instance, in this case, if we assume that that's the right notion of a junction, what does it mean for an object in my infinity cosmos to have a terminal object or an initial object? So of course what that would mean is that we would need, so our infinity cosmos has a thing called 1, which is just the terminal object in the infinity cosmos, and there is, of course, then a unique map from any object of this infinity cosmos, which I'm just going to refer to as an infinity category, to 1. And we might imagine that, were my wild conjecture correct, that the correct notion of terminal object for an infinity category would just be to say it had a right adjoint. So this map from A to 1 had a right adjoint in this peculiar homotopy 2 category. Now, of course, what that means is that there's some data that represents this. So what it would actually mean, in particular, is that we have a map from 1 to A, which is just an infinity functor, an arrow of this infinity cosmos. We have a 2-cell, which is a natural family of maps, or it's actually some kind, because we're working in this quotient 2 category, it's actually some equivalence class of maps, but we don't worry about that too much. That goes from the identity on A to T composed with the map into 1. And then we need to assume that the component of that, so precomposing with something, gives me the identity. This is the sum. So if I precompose this thing by 1 into A, so this map T, then that thing has to be an identity. That's so this is actually one of the definitions that we often give of what it means to be a terminal object. A terminal object is something that has a cone from the whole category to the terminal object whose component at the terminal object itself is the identity. That's all this. So, I mean, that seems to make sense. That makes sense from a 2-categorical perspective. But what you can actually do as an exercise is you can look in the infinity cosmos of quasi-categories. So this is the sort of canonical, so in the same way that the category of categories is the canonical 2 category, the category of quasi-categories is the canonical infinity cosmos. You can look in there, and you can take the equivalent specifications on the previous slide, and you can do some calculations, and you actually discover that a thing in a quasi-category is terminal in the sense of the former slide, precisely if it has a lifting property that looks like this. So what this lifting property says is that if I'm given the boundary of a simplex whose final vertex is the terminal object, then I can fill the boundary of that simplex in with a simplex. Okay. So I guess the easiest one of those to see is the boundary of a 1 simplex is just 2 points. If the second of those points is the terminal object, then I can fill in those 2 points with a simplex, which is just an arrow going from the one that's here to the terminal object. The higher filling conditions ensure that can be done in a coherent way. So for instance, if I have the boundary of a 3 simplex whose final vertex is T, then what that gives me is essentially I've got a choice of the map from the first object to T, I've got a choice of the map from the second object to T, and I've got a map between the 2 objects here. And what I'd usually say in category theory is that the maps to the terminal object are unique. Well, I can't say that in this case because we're in quasi-category theory, but what I can say is that there's some 2-cell showing that the quasi-categorical composite of this and this is the same as that. Okay. And what you'll find is that this is exactly the definition of terminal objects in a quasi-category that Joyal gives in his paper on quasi-categories that he then uses to define what it means to be a limit. Now, what we can do immediately is we can apply some. So this is already a win. Terminal objects are the right thing. That's good. That gives us hope that maybe some of the other things we're going to talk about are the right thing. So what are the immediate consequences of this? So the first immediate consequence is that terminal objects are going to be preserved by right adjoints, which is not necessarily an immediate result from Joyal's definition of a terminal object and Lurie's definition of what it means to be an adjunction. There's a bit of work to be done there. Whereas here, this is a triviality for 2-category theorists because we know in any 2-category, adjunctions compose. So if I take the adjunction defining the terminal object and I take the adjunction of which this right adjoint is part, I can just compose those 2 adjunctions And the composition of those two adjunctions is another adjunction, which demonstrates that the terminal object goes to the terminal object. Okay. I can also show that in an arbitrary infinity cosmos, terminal objects are defined representably. So what that means is that if T is a terminal object, so in other words, if I've got a map from 1 into A, and it has this property that's right adjoint to the unique map going back in the other direction, it's going to have that property. So if I'm given a map from 1 to A, it's going to have the property of being terminal, precisely if the corresponding thing which I get by going from B to 1 to A is terminal in the functor quasi-category. So in other words, for each B, make this terminal object an arrow of this functor quasi-category from B to A, just by precomposing the unique map into 1. That thing is going to be terminal inside here, and vice versa. So in other words, what this representability thing just means is it's the usual thing that we do in category theory that says, for instance, a limit is representable because we know that something is a limit precisely if I apply if I apply the Onager embedding to it, I get a limit. But I guess if I look at it Hom-wise, limits give me Hom-wise limits in sets. That's exactly what this is. So this notion is entirely representably defined. And we can just get that again from, so this tells us that not only is this the right notion of terminal object in quasi-categories, but it's also the right notion of terminal object in the infinity cosmos. Okay, so how do we then do limits and colimits? Well, we can do those entirely analogously. So what we can do is we can say, okay, well, so the first thing we need to do is decide what do we mean by a diagram in this case, and there are two possibilities. So in the axiomatic framework that I've given you so far, we've only assumed that, we haven't assumed, I guess if we were going to do the usual definition of limit or colimit, we'd say, okay, well, I'm going to take my diagram shape X, I'm going to take my category that I'm going to take limits in A, and I'm going to form a functor category from X to A, and then there's some adjunction between that and A. So the first question we have to ask is, what's the functor category X to A? And because we're in an abstract setting, I can't just assume that that exists, that has to be part of the axiomatics. So we do already have in our axiomatics one notion of diagram, which is given to us by the cotensor. So if I'm given a simplicial set, and I'm given something in K, then I can form A to the X, which I can think of as X-shaped diagrams in A. So they're actually diagrams in A, but given the shape of a simplicial set. Okay. So that's one notion that we can have here. The other notion we could have is we could go one step further and we can add an extra axiom to K. We could actually say that K was Cartesian closed. So quasi-categories are Cartesian closed, for instance. And so then we could talk about sort of, so I guess this is a sort of external notion of diagram, sort of external relative to simplicial sets. This is an internal notion, but I've internalized entirely. But the presentation is exactly the same whichever one you want to do. And in fact, for most purposes, when we're starting out this elementary stuff, we're just interested in simplicial sets, shaped diagrams. Because things like pullbacks are what we're going to be interested in. Okay. So then what we can do is we can simply say, well, of course, the axiomatics gives me a functor from A into A to the X, because either it's a property of cotensoring that I can always get a map like this, or it's a well-known property of Cartesian. If I've got a Cartesian closed category, I can take a projection from A cross X to A, and then I can transpose it and I get a map here. And I can ask for that to have left and right adjoints, or left adjoint or right adjoint. And that would be a perfectly reasonable notion of limit or colimit. And again, essentially, as a corollary of the thing that we did for terminal objects, you can prove that this is the same as Royal's notion of limit or colimit. Although we have to think, I mean, there is a little bit of a difference, which is the cones that are involved in this construction are what's known as fat cones in Royal's. So Royal has a notion of, well, he has a notion of cone, which is based upon the join operation in simplicial sets, and he has a notion of fat cone, which is based upon the notion of product. So you do product with I, and then you sort of munch down one end. They're not exact. In category theory, they're exactly the same thing. In quasi-category theory, they're slightly different, but they're equivalent. Because of the way that we've set this up, this is going to be the fat cone version, but then our theorem gives us equivalence with the Joyal cone version. So, but it's worth pointing out that if we're trying to enrich in this way, we're always going to get fat notions, not thin notions. Okay, so we can do that. And an example might be pullbacks. And for this, simplicial sets are enough. So I just take the obvious simplicial set, which I guess the notation we've used is something awful like this. And maybe we'll change that by the time the book's published. Which is just the simplicial set that has 3 vertices and 2 simplices, both of which are ending in one of the vertices. And I guess it's the push out of a pair of 1 simplices along their common codomain. That's the word, thank you very much. And so we could say, and this is certainly enough, in any infinity category, in any infinity cosmos, to describe what it means to be a pullback in this case, because we can ask that the infinity category A has all pullbacks. That just means that this adjunction exists. Okay. And the way to think about this is, it's very much like the way that we think about pullbacks in category theory, except we have to remember that when we're talking about cones and our pullbacks, that actually a cone, in a normal pullback, we just say, well, a cone is just something this commutes with this. Whereas in a quasi-category, we do sometimes have to worry about the fact that commuting means there's some choice of data that shows that it commutes. So you've got a specific choice of a pair of 2 simplices that demonstrate that this arrow composed with that one is this, and that this arrow composed with that one is that. And those are all parts of the structure. So sometimes the difficulty in working in quasi-categories relative to categories is you've got to remember some of that homotopy theoretic structure, unless, and actually what the infinity cosmos structure allows us to do is sometimes to forget that fact. Okay. But of course what we might want to do is we might want to do something a little bit less than that. So what I'm going to try and do, I'm not sure what time I'm going for time. What I'm going to try and do in the last 15 minutes is try to motivate for you how we might talk about stable infinity categories, so the place where we do stable homotopy theory. Okay. So the first thing that we need to notice about stable infinity categories in the first instance is that maybe we don't assume that they have all pullbacks or all pushouts or something. We're going to only assume that there's some particular set of pullbacks or pushouts that we're interested in. In fact, what we're going to start with is we're just going to start with a situation in which we're going to have a pointed infinity category. So a pointed infinity category in this context just means an infinity category that has an object. So when I say an object in infinity category, I just mean a map from 1 into that object, into that infinity category A, which we'll call star in this case. And what we want star to be is both initial and terminal. So if you remember in sort of like a topological space, if I have pointed topological spaces, then the 1-point space becomes both initial and terminal. So the way to think of this condition is really to say, I've now got an infinity category whose objects look as if they're pointed spaces. Okay. So I can certainly define that, and that's defined just in the language of what we've done before. We have terminal objects, we can do that fine. We can define what it means for a particular map to be both initial and terminal, that's wonderful. But what we'd like to do is we'd like to talk about loop spaces and suspensions. And loop spaces are a particular form of pullback in this context of infinity categorical pullback. So in particular, the way that I form loop space is if I'm given A, and now think of A as an object inside one of these. So again, we're doing the category theorist trick of saying an object inside an infinity category in a cosmos A is really a map from some other infinity category into A. So maybe it's from the terminal infinity category into A. So we're using the notion of generalized elements to understand the internal structure of something. So if I'm given an A, then of course the initiality of this 0 object, this star, ensures that there is a map from star into that A. That's given to us by the universal property. So I can take 2 copies of that map, and I can form the pullback, or I can hope to form the pullback, And that thing is, well, so the important point is that because we're doing infinity category theory here, that thing is not to be thought of as the usual pullback. That thing is to be thought of as a homotopy pullback. So in other words, the squares that determine that pullback aren't just commutative, they have a homotopy, a given homotopy in them. And of course, if we're taking a homotopy out of star, we really think of that as a loop in the space from that base point to itself. So this is genuinely, so if we do this in the quasi-category spaces, this is genuinely the usual loop space. And dually, we can take this push out, and that will give us the suspension. And we'd like to be able to say, I only want these push outs and pullbacks. And very quickly, we can do that because we can introduce another notion, a notion related to a junction, which is the notion of an absolute right lifting. So I'm not going to go into the details of this, but the idea is that this is some kind of relative adjunction. I've got a functor, and I'd like to assume that it has not all things universally that we might expect would be universally determined by its adjoint, but only some collection. So only some collection of maps in the codomain, of objects in the codomain, actually have, say, left or right adjoints. And the way to do this is, it's really kind of like a dual Kahn extension property. So it says this thing here is an absolute right lifting if for any square like this in the 2 category, it factors uniquely like that. And it turns out that we can use this notion in exactly the same way as we use the adjunction notion. It's also very well behaved in this 2 category, and we can use that to say that, so we can define a family of diagrams to just be a map from I into A to the X. So it might just pick out one diagram. So if I was just the terminal object, then it would just pick out a single diagram. If it was A itself, then this might pick out, if it was A itself and X was the pullback thing, then this might pick out one pullback for each A with just the thing in the right-hand corner. And it turns out that if I say that this thing is an absolute right lifting, then that's the same as saying that this thing has limits for each thing, but just in this family. And the calculus of these is very similar to the calculus of the junctions. So for example, another exercise you might want to try is you can again prove preservation by right adjoints of this notion of limit, and you can prove that it's the right notion. So, so we can narrow down, we can actually say, I just want limits, in this language we can say I just want limits for those pullback diagrams that are going to give me loop spaces, or those ones that push out diagrams that will give me suspensions. Okay. And I should stress at this point, this works in any infinity cosmos. So we're not just talking about loop spaces in the infinity cosmos and quasi-categories, we're talking potentially about loop spaces in fibered infinity categories over some base. So what I would like to do is explain very quickly so one of the things that's famous about loop spaces and suspension is that if I define them in some suitable way, they should be adjoint to each other. So let's see if we can do that. So the first thing that I might note as a technical thing is that we can actually rephrase this lifting property. So the lifting property that we had before, so this was the limit definition that we just did on the last slide for some family of limits of shape X. It turns out that I can prove that this absolute right lifting exists if and only if a related one does. So what I can do is I can take X, which is my diagram shape, I can give it a new initial object, and that is what we call X left triangle, to give it a new initial object. So of course now there's an injection from X into X with a new initial object, and pre-composition by that gives me a map from diagrams of shape X with an initial object to diagrams of shape X. And then I can ask for this thing to have a lifting. And it turns out in exactly the same way as in category theory. So this is the theorem that says a limit can be turned into a Kahn extension over a diagram that has an appended initial object. Exactly the same thing is true here. So a family of limits exists over here precisely if I have this lifting, and in particular where that thing there is going to be an identity. So the important thing about the loop suspension adjunction is that, first of all, I'm assuming that in having loops and suspensions that I've got some, well, an absolute right lifting and an absolute left lifting that defines loops and loops and suspensions. And then what I can do is I can convert those into this form over here. And the important thing to notice is that the left triangle of the diagram that defines pull-outs is the same thing as the right triangle of the diagram that defines push-outs. They're both the square. And so therefore, these two adjunctions, or these two semi-adjunction notions, share the same, well, domain or codomain, whichever way around you look at it. And so what I actually get is I get a diagram like this, in which just this is an adjunction that describes the, I guess this is a right count extension, so that describes loops, and this one here describes suspensions, and I again use my theorem that says that adjunctions compose in the two category, and I get an adjunction, which is the loop suspension adjunction of the usual form. So really, really simple. Nothing here to see, really. So I'm not going to quite get on to what I want to say, but I want to say just a few more things about adjunctions. So there are all sorts of things that I will say quickly. There are slides later on that I won't get to, but there are a whole range of results that we can prove about this that are essentially just two categorical and that are important things about stable infinity categories. So we can basically do, sort of with the machinery that I've talked to you about so far, we can basically do the fundamental theory of stable infinity categories using this as a guide. So I won't define what stable infinity categories unless we have time, but suffice it to say, this is the basic information on which we will work from. Okay. What I actually want to say is that there are a couple of other presentations of adjunctions that are very important. So if we were only interested in category theory of adjunctions, the world would be a very boring place because not everything is an adjunction. And there are other things that we want to describe in category theory, or there are other ways that we want to describe things, and we'd like a jumping off point for those. And so maybe one of the jumping off points is to think about other ways in which we can describe adjunctions. And that will give us a jumping off point, for instance, into the world of profunctors, which are an important thing. Okay, so the first thing to say is that for an infinity category, so inside my cosmos K, I can define what it means to be the Hom space, or to be a Hom space of that infinity category. So the way that I do it is that I can form A to the 2, which is just because I have it. So 2 is just, well, that's another name for the 1 simplex. So I can do A to the 2 because I can take any infinity object in the infinity cosmos, raise it to the power of some visual set. I can then take its 2n projections, and if I'm given a pair of objects in A, so remember, objects in A are just maps out of some other object into it, so it's a generalized element. Then what I can do, so if I'm given F and G, then what I can do is I can pull back along G cross F, this thing, and I'll get something over here that we'll call Hom of A from F to G. So think of F and G as objects of A. This should be thought of as the Hom space between F and G. And in fact, an exercise will show you that if we think in the sliced cosmos over C cross B, this thing up here is actually a space, where space means, again, if I look at generalized elements into it, or if I look at if I Hom into it by each other object, then that Hom space is not just going to be a quasi-category, it's going to be a Coulomb complex. So, as you might hope from Hom spaces in an infinity category, they are actually, well, when considered over C cross B, they are actually spaces. Now, what you can get from this information here is you can actually write down a structure inside the homotopy 2 category. And so that structure looks like this. So we've got F and G, which are our two maps from C and B into A. And then we've got these two projections. Well, I've got the composite of this map with these two projections, which gives me a pair of projections here. And then this map here actually corresponds to a one simplex in the Hom from there to there, which is essentially going to give me a member of an equivalence class that determines a 2-cell from here to here in the homotopy 2 category. So if we're 2 category theorists, then this is a structure that we're very familiar with, because I'd say, well, this is a comma square or something. I've got a pair of fixed maps F and G, and I'm looking at a vertex here plus a pair of maps and a 2-cell in there. And comma squares are used in 2 category theory to describe the comma construction in category theory. So if we want to take comma construction in category theory and we want to generalize it to a 2 category, we do that by taking comma squares. And they have a nice 2-dimensional universal property that characterizes them. So we might ask in this case, well, if we accept that comma squares are very important, that there's all sorts of category theory we can do with them, then we need to understand these squares here to understand what infinity category theory we can do with them. So let's have a think about what the universal property of this thing in that homotopy category is. So the first stumbling block in this whole program is that these things are not comma squares in the sense that 2 category theorists would have originally defined them. So a 2 category theorist would say something like, well, if I'm given another square of that shape, then there's an induced 2 functor, I'm induced 1 cell from its vertex to the comma. And then it would say something about, given a pair of 2 cells with a certain commutativity property, that induces a unique 2 cell between the induced 1 cells. It's not actually true that that universal property works in the homotopy 2 category because we've quotiented something out. We wouldn't expect that to be the case. But in fact, it turns out that this thing has a property which is almost as good. So it has a weak property that says, so the way to understand the universal property is to say, okay, well, that square on the previous slide induces a map from, so if I look at maps from U into P here, or if I look at the function space from U into P here, then I can compose on with P0 and compose on with P1. And that gives me things from here to here and here. And in fact, what I get is I get a comma square in cat. And that induces something into the comma. So I get an induced map like this. Now, the usual universal property would say that that induced map is an isomorphism. And maybe if we were bi-category theorists, it might ask that it was an equivalence. That would be equally good. But in fact, we're even weaker than that. So this map is something that's called a smothering functor, for want of any better name. So the properties it has is it's surjective on objects. The second property it has is its form. So if I'm given a map in here between the images of 2 things here, I can pull it back to there. But it's not, that pullback isn't unique. I mean, there may be many ways of doing that. But then the other thing is that it's conservative. So that means that if the map over here was an isomorphism, it gets pulled back to here, and I get another isomorphism, essentially. And it turns out that this is actually more than adequate for doing a whole heap of things. So for instance, weak comma squares are unique up to equivalence, because I can induce maps, and if I've got 2 candidate weak comma squares, I can induce maps in either direction, I can induce 2 cells between their composites, and then I can show that those 2 cells are isomorphisms using the conservativity property. So these are better than the weak universal property in the usual homotopy theoretic context, because they are actually defined up to equivalence. So it turns out and we can apply that property, and we can do a bit of 2 category theory with it, and we can actually show that, so first of all, we can make a definition, which is we can say that something of this form, Hom Fg into there, so this Hom, is left representable if there exists an L from B to C such that this is true. So think of this as, I mean, these are profunctors or something, really. So this is saying that this profunctor is left representable. We can say that it's right representable if we have something going the other way around. And then it turns out we can say that a functor U has a left joint in the previous sense precisely if hom BU is left representable. So this is already starting to look like a calculus of profunctors. It's describing now a junction, not in terms of equational properties, but in terms of representability properties fibered over some base. And there's a whole theory of Cartesian and co-Cartesian fibrations in this context that I won't bore you with. But it fits in here. These things are modules in the appropriate sense, and we can work with them nicely. Okay, so that's the hom-wise character of junction. So maybe what I'll conclude with is just to say, what we've really talked about today is 3 views of junctions and their applications to something. We found rather remarkably that the 2-categorical notion in this homotopy 2 category of a junction gives rise, as a 2-categorical, actually just a 2-categorical argument, to a notion of module and of representability, and that the characterization, there is the correct characterization of a junction in terms of modulus and representability. Finally, we've also found that representably, these are junctions of the right kind, in the sense that representably, these are the junctions that Verity gives. The advantage is that we've used a little bit of 2-category theory to tame some of that. One thing that I haven't talked about in this, well, a number of things I haven't talked about this because there's about 3 slides left, but one of the things I haven't talked about is that apparently this is just a 2-dimensional structure, right? I've described my junctions just in a 2-category. It seems to be entirely 2-categorical. Naively, I might think, well, that's the wrong notion, because presumably the notion of a junction in the infinity categorical world would have some unit and co-unit, and then would have some maybe my triangle identities were mediated only up to homotopy, and then those homotopies would have to have homotopies between various composites of those, and so forth. So I had to get a whole coherent structure of a junction to work with. So one question we haven't looked at here is the question of homotopy coherence. Can I get some kind of homotopy coherent notion of a junction from this one? And it turns out that you can. So what you can do is you can build, just from this basic data, an entirely homotopy coherent structure that contains all of that complicated coherence information using the universal property of the junction, and you can use that to build a theory of monads and monadicity. So that then becomes, again, a formal consequence of these kinds of axioms in this context. There's plenty more to say, but I might refer you to the 500 pages that already exist of this awful book that we're writing. And I hope to have my fingers crossed that when I'm in Baltimore in the next 5 weeks, we might add a couple more pages to it. But thank you very much for your attention.
Any questions for the speaker?
When you said you could prove like the basics of the theory of stable infinity categories from that definition, what does that include? You can prove that finite limits can be finite co-limits
and things like the various different characterizations of them. Right. So I prove that they're finitely complete and co-complete. The characterization, I mean, the important characterization that says that a pointed infinity category is stable if it has kernels and the loop spaces, space functors and equivalence, for instance, is something of this. And then the stabilization process, so cosmos. Right. So once you have that, what you can show, so once you've shown that a stable, so I haven't actually defined for most people what a stable infinity category is, but the way to think of it is it's a structure that has, it's an infinity category, it's got a point, and then every map has a notion of co-kernel, so that's a push out against the map from its domain into star, and it has a kernel which is a pullback of the map from star into its codomain. And then it asks, that if I've got the diagram that defines a kernel is also a co-kernel and vice versa. And an important characterization of that is that that's the same thing as saying that I've got a pointed infinity category that has kernels. Now, once I have kernels, I can define the loop space functor, and one would expect for the loop space functor to be an equivalence. And it actually turns out that being a stable infinity category is the same thing as saying I've got kernels and the loop space functor is an equivalence. So we can prove the equivalence between those notions in this context. So once you have that, then you can prove that the subcategory of stable infinity categories is itself an infinity cosmos. Right? And infinity cosmos is, so one of the axioms that I didn't dwell on is that infinity cosmos is, we assume that they have limits of countable chains of isofluctuations. So the way that you, so that means that you've got, the way that you get the stabilization, so in other words, just given something that has, say, finite limits and a point, you want to make a stable infinity category from it. The way that you do it is that you take this thing and you take its loop functor, and you take the chain, which is just apply the loop functor over and over again, and then you take its homotopy limit. And you can do all of that in infinity cosmos. So infinity cosmoses support the theory of stable infinity categories up to and including every object has a free stabilization. And that stabilization is essentially the spectrum construction. So that works whether you're fibered, whether you're in one of these other exotic models, whether you're in an infinity n category world. Yeah.
Any more questions?
Why is inflation set? I mean, it seems this is a deliberate choice that you do to model the rest of things.
I mean, so ultimately you could start with any infinity 2 categorical model and do a similar thing. And the 2 category theory works out the same way. So you get the right notions of a junction and so forth. The issue, I mean, the reason for choosing this particular one, well, so unfortunately most of the infinity 2 category models that we use at the moment are at some level simplicial. So even sort of beta 2 sets or something. I mean, at some level it's simplicial. But the models that are less simplicial are less familiar to people. So really it's a pedagogical choice, not a mathematical choice. Because we wanted to pick a model that we felt that in most people in the target audience, which is unfortunately not category, I mean, it is category theorists, but it's less category theorists because, I mean, if I was talking, if somebody like George Jan Lidson was in the audience, right, his comment about this would be, well, that's all very good, and I'm very happy that, well, this is the comment he's actually making. This is all very good, and I'm very happy that you're making this into what he regards as category theory, but he still regards it as rubbish, right? So this isn't necessarily designed for a category, but for an audience of category theorists where we might do something completely different in our infinity 2 categorical models. It's really designed for people who come from a sort of emerging, I mean, it's really designed for people who already are relatively happy with quasi categories, or at least what they are as functions. So it's not fundamental to this, it just happens that history means most of our models are simplicial.
It does mean that it has a practical advantage that if you want to turn an existing model into an infinity cosmos, it's less work for most of them because they're already like that.
Yeah. I mean, what it really means is that you can take people's existing sort of baseline knowledge of what a quasi-category is, which most people in this audience would have, and you can kind of bootstrap that up to tell them that they actually know a lot about all sorts of other models that they didn't think they knew anything about. So, but sort of overt commitment to any particular model is not a good idea, hence we do things synthetically.
Why do you choose the word synthetic instead of formal, like formal category theory?
Oh, it's just fashion. As long as they're in cycles.
Yeah.
I think it might be that maybe I used the term formal in the last grant application.
Oh, right. So it works.
I mean, I think it also changes. I think that the earlier stuff we did was very clearly formal category theory. I think the developments that we've been working on more recently are moving more towards something that looks a bit more like synthetic accounts of, say, differential geometry or something. That's possibly why this ship is okay. But it's just fashion.
Why the word cosmology?
Oh, so that's not mine. So I guess that people like Ross Street and Max Kelly. So Max Kelly originally used the word cosmos to describe a particular sort of well-behaved, well-structured kind of monoidal category over which he wanted to enrich things. It's a monoidal category in which basically so many good things are going on that most of sort of ordinary category theory can be adapted across to enriched category theory. He called it cosmos. And then Ross Street came along building on that and said, well, maybe a cosmos is the cosmos isn't the thing that we're enriching over, it's the two category of the structures that we've enriched that has all of these nice properties. And so he started talking about axiomatic cosmoi, which were the place that did sort of abstract category theory. So when we came to this, we just used to call these, I don't know, Joya enriched categories of vibrant objects. But that got a bit too long to say. So I think one of us was giving a talk, and Peter May was in the audience, and he said, well, since these Australians have used the word cosmos, why don't you use that? So that's this kind of long history.
Any more questions? So we think again, I will speak.